Hey everyone, ever heard that we'll make Mars our next home? It sounds like a thrilling future, a testament to human ingenuity. But before we can even consider establishing a permanent presence on the red planet, we must first overcome the monumental hurdles of simply getting there and surviving. This journey is far more complex than any lunar mission. Stick around, because we're breaking down why a trip to Mars might just be the biggest challenge humans have ever faced, demanding unprecedented scientific and engineering solutions. The sheer scale of interplanetary travel is difficult to grasp. The Moon, our closest celestial neighbor, is approximately 240,000 miles away. Apollo missions reached it in roughly 3 days, with launch speeds peaking around 25,000 mph to escape Earth's gravitational pull. This was a sprint compared to the marathon required for Mars. Mars, at its closest approach, is about 34 million miles from Earth. This is over 140 times farther than the Moon. Even with our most powerful rockets, a journey to Mars typically takes between 7 and 9 months. This extended transit time is not just a matter of endurance. It's a fundamental challenge for life support, resource management, and human psychology. Interplanetary travel isn't a straight line. It's a complex dance of orbital mechanics. We utilize what's known as a Hohmann transfer orbit, an elliptical path that conserves fuel by using the sun's gravity. This trajectory dictates a long, slow cruise, making sustained high speeds impractical and inefficient. Imagine being confined to a small capsule for nearly a year, far from any immediate help. The alignment of Earth and Mars is crucial for efficient travel. Both planets orbit the Sun at different speeds and distances. This creates specific launch windows when the planets are optimally positioned for a fuel-efficient trajectory. These windows occur only once every 26 months. Missing a launch window means waiting over 2 years for the next opportunity. This strict timing dictates mission planning and crew rotation. A round-trip mission to Mars would involve approximately 9 months of travel to Mars, followed by a stay of around 17 months on the Martian surface, waiting for the next return window. The return journey would then take another 9 months. This means astronauts would be away from Earth for a total of 2 to 3 years. Such an extended duration places immense demands on spacecraft reliability, life support systems, and the psychological resilience of the crew. It's a commitment unlike any other space mission undertaken. Upon arrival, Mars presents a hostile environment. Its atmosphere is incredibly thin, with a pressure less than 1% of Earth's. While thin, this atmosphere can still generate powerful dust storms with wind speeds exceeding 60 mph. These storms can last for weeks or even months, engulfing the entire planet. The fine Martian dust, composed of abrasive silicates and perchlorates, is a significant hazard. It can infiltrate mechanical systems, abrade equipment, and coat solar panels, severely impacting operations. This pervasive dust also poses a health risk to astronauts, potentially causing respiratory and other issues if not meticulously managed. Temperature extremes are another critical challenge. While daytime temperatures near the equator can occasionally reach a balmy 70 degrees, 20 degrees C, nights plunge to a frigid 112 degrees, 80 degrees, or even lower. Designing habitats and equipment that can withstand these drastic temperature swings, day after day, requires advanced materials and robust thermal engineering solutions. Mars is significantly farther from the Sun than Earth, impacting solar power generation. Solar panels on Mars receive only about 40% of the sunlight intensity they would on Earth. Furthermore, the frequent dust storms can quickly cover solar arrays, drastically reducing their power output and requiring constant maintenance. Reliable power is essential for life support, scientific instruments, and communication. To overcome the limitations of solar power, future Mars missions will likely require more robust energy sources. This includes advanced battery storage systems to last through the long Martian nights and dust storms. Nuclear power, specifically radioisotope thermoelectric generators, RTGs, or small fission reactors, offers a more consistent energy supply. However, these systems are incredibly heavy and expensive to transport. Developing lightweight, safe, and powerful energy solutions is a critical engineering hurdle for sustained human presence on Mars. Mars currently lacks liquid water on its surface, due to its low atmospheric pressure and cold temperatures. While water ice exists in the polar caps and subsurface, extracting and purifying it for human consumption and agriculture is a complex process. The Martian soil, or regolith, also lacks the organic nutrients necessary for Earth-style crops. Establishing a self-sustaining outpost requires sophisticated closed-loop life support systems. This includes advanced hydroponic or aeroponic greenhouses that can grow food using minimal water and nutrients. These systems must be fully sealed, climate-controlled, and capable of recycling air and water with near-perfect efficiency. Any failure could be catastrophic. Resupplying a Martian base from Earth is incredibly costly and logistically challenging. Sending enough food, water, and spare parts for a crew of even a few astronauts for a multi-year mission would require dozens of massive rocket launches. This underscores the critical need for in-situ resource utilization, ISRU, the ability to live off the land by extracting resources directly from Mars. One of the most significant threats to human health on Mars is radiation. Unlike Earth, Mars lacks a global magnetic field and a thick atmosphere to shield its surface from harmful cosmic rays and solar particle events. Astronauts would be exposed to significantly higher levels of radiation during transit and on the surface. This radiation can cause severe long-term health effects, including an increased risk of cancer, damage to the central nervous system leading to cognitive decline, and vision impairment. Protecting astronauts requires heavy shielding, which adds significant mass to spacecraft and habitats, making them more difficult and expensive to launch. Beyond physical health, the psychological toll of extreme isolation, confinement, and the constant threat of a hostile environment cannot be underestimated. Maintaining crew morale and mental well-being over a multi-year mission, far from Earth, is a critical challenge that requires careful planning and support systems. Dreaming of life on Mars is an inspiring vision, pushing the boundaries of human ambition. However, the truth is, we must first solve an array of unprecedented challenges. Overcoming the vast distances, enduring the harsh environment, generating sustainable power, producing our own food, and protecting human health from the ravages of space. These make lunar missions seem like backyard camping trips. Before we can truly pack our bags for a new home, we must tackle these hard scientific and engineering problems. Right now, setting foot on Mars could indeed be a one-way ticket without these solutions. If you're fascinated by the intricate details of space exploration and the monumental challenges humanity faces, hit subscribe to explore Diversion Universe. Smash that like button to support more deep dive breakdowns, and drop a comment below. What Mars myth or engineering hurdle do you want us to explore next? We've got you covered as we journey through the cosmos.